Well, welcome back. Nice, bright, sunny morning. I thought, gee, the weather's better. We'll have more people here today. Attendance of 2. That's kind of depressing. So, if you're out there in virtual land, please come to class physically. I would appreciate that. All right. So today I want to wrap up Chapter 2. I know there's several more things in Chapter 2 after this section 2.11, but they're pretty minor, and so you can pretty much just read those yourself, so I won't belabor them. But the one thing I'd like to finish today is section 2.11 on matrix permutation. And so we looked last class at how to do a general permutation of a matrix, of a square, rectangular, unsymmetric matrix. And today what I want to look at is, well, what if A is square? Then it turns out if you write this linear algebraically to permute a matrix symmetrically, if you have a row permutation P, to apply that same row permutation to the columns of the matrix A, you need to post-multiply by P transpose. And in MATLAB notation, you can also write this way. If P is a permutation vector. And wow, we've tripled our attendance. This is great. All right, so what Sparse does, though, for symmetric matrices is it's also kind of like what MATLAB does for its symmetric matrices, but slightly different. When you do this in MATLAB, if you say do a Cholesky factorization of a matrix, what it actually is doing, it's only looking at the upper triangular part of the matrix. It's assuming you're passing into it a symmetric matrix, that is to say A equals A transpose. And so it's only going to look at the upper triangular part, and it's going to assume that, well, either you know it's symmetric, or you've only stored the upper half, or whatever. It just ignores the lower part and assumes that the lower part is the transpose of the upper triangular part. On the other hand, in MATLAB, if you do this, so that's one way MATLAB handles its symmetric matrices. If it's supposed to be symmetric, if it must be symmetric, then it says, oh, just look at the upper half. If on the other hand you do this in MATLAB, and the matrix is not exactly symmetric, okay, that is, if this doesn't hold precisely, and it's not approximate. I had someone send me email once. I get a lot of questions, for over email over stuff in MATLAB because a lot of it's my code for Sparse solvers, and this guy was concerned, why isn't my backslash using a Cholesky factorization? I've got a symmetric matrix. Well, he sent me the matrix, and I looked at A minus A transpose, and I got results of order epsilon, 10 to the minus 16. I said, well, that's not symmetric. He said, well, it practically is symmetric. No, it's not exactly. Down to the last bit, it's got to be symmetric. So it looks at this, is it symmetric? And there's actually a meta-algorithm here that's quite interesting to decide how to solve a linear system, whether it's sparse or dense, whether it's symmetric or not, whether it's rectangular, and sometimes it'll try one method, and if that fails, it'll try another one. It's a very complex meta-algorithm just with that one little backslash. I once had a colleague at Sandia National Lab talking about his computational science problem, and he was talking about this large matrix problem, and then he was talking about some small submatrices on the diagonal, and he said, well, it doesn't really matter how you solve that. I mean, you could just use backslash. And my eyes kind of went up like this. And so you just realize you've invoked about 250,000 lines of code I'll just use backslash. Oh, okay. Anyway, so this is how MATLAB handles its sparse matrices, and Sparse is kind of similar. If you pass in a matrix to one of the codes that expects a symmetric matrix, then it only looks at the upper triangular part, and it ignores the lower triangular part. So it's different than this. But if you're calling a code that has to take as input a symmetric matrix, then that makes some sense. Rather than to check, it's kind of expensive to check. So that's what my code does. In fact, so you don't actually even have to store. This can be empty. You don't have to store the lower triangular part. Well, that's all well and good, but what happens if you come along and do this? If you do this and decide that, okay, this is the entry in, say, row 3, column 5. Let's see, does that make sense? Yeah, so it's right here above the diagonal. Okay, it's quite possible. Now, of course, there's an implied entry below the diagonal. But with the permutation, it's quite possible that this specific entry could go down here somewhere. I mean, what if, for instance, the permutation says to swap, symmetrically swap, say, let's see if I can do this correctly. Say swap rows 3 and, I'll do this symmetrically. I'll do this with 3 and 5. Suppose the permutation says only to swap rows 3 and 5 and columns 3 and 5. Well, if you do that, if you swap these 2 rows, let's see, this goes down here and then this goes over here. So this entry would actually go below the diagonal. And then the entry that was down below would go up here. Okay. Now, that, of course, has no effect on that particular entry. It does affect all the other entries in the matrix. And so that's not a problem if you've got both parts of the matrix stored. Then you can just use this regular code, just put P and Q the same. It'll work just fine. You give it a symmetric matrix. If P and Q are the same, you get back a symmetric matrix and everything is happy. But if you store just the upper half of the matrix, then you'll have elements, and you only expect the upper half to be of interest, of importance. Then you'll have elements that disappear into the lower part, and then they're gone because you ignore them. So in the code then for permuting a symmetric matrix, and so because of this, I had to write a special code that permuted symmetric matrices, assuming that only the upper half is either stored or the upper half is of interest, and the lower triangular part is ignored. And that's this code here, this symmetric permutation, and it's got the prerequisite, all the jazz here to allocate the output and such. One thing that's interesting about this, because I'm expecting a symmetric matrix on input, I don't even check to see if the thing is square, let alone symmetric. You notice I don't even get the number of rows of the A matrix. Okay. So if you give it a rectangular matrix, say of this size, I'm going to say, well, that's the matrix you're looking at right there, and I'm going to treat that as the upper triangular part of a symmetric matrix as on input. The lower half is ignored, whether it's rectangular or not. Then there's just a minor twist then. So it acts much like the symmetric permutation part. I mean, there's except that we have to take 2 passes at this. Let's see, where's the keyboard? There we go. The reason we have to take 2 passes is because when you're just permuting a regular matrix and you're just column-wise, you're just moving the columns around. And so it's very easy to determine how many non-zeros there are in each column of the output. It's just a permuted version of the input. So you don't have to go count to decide to set up your new data structure where things go. Okay. But it's when you're dealing with a symmetric matrix with the only upper triangular part is stored, then the column counts can change dramatically. I mean, for example, I could have a matrix that looks like this. It's got a dense row and a dense diagonal, and it looks like that, but only the upper part is stored. So every column has exactly 2 entries in it. Well, except for the first one, which says 1, because you don't store this, say. Well, if you were to swap this symmetrically, suppose you swap column 1 and n and 1 and n, then suddenly you have this matrix, and now every column of the matrix has 1 entry except the last one, which has n entries. Okay, so the first thing you've got to go through then is count the thing and to find these column counts. And that's what this is doing here. And so it's taking as input because I'm going through row indices, I need to convert the old row to the new row indices. I need the permutation inverse, the pinv. This, by the way, is not to be confused with the pinv command in MATLAB, which computes the pseudo inverse, which has nothing to do with permutations. So I've got to first go through this pass here and determine, well, I'll get a row index. If it's in the lower triangular part to start with, I have to ignore it. So there's a continue statement there to skip the rest. Otherwise, this is an entry of interest. It's in the upper part of the input. and I've got to permute the thing. So I've got to figure out I've got the new column index, J2, and the new row index, I2. And now this is an entry I want to keep. And so if it happens to go below the diagonal, I've got to put it back up to the top part. So I've got to take the I2 and J2 and take the larger one as the column index, and the smaller one is the row index. So that's why there's a max here of these two. And then, so this counts the number of columns, entries in each column, and then there's a cumulative sum to find the column pointers. I use this over and over again, this cum sum function. And then the second pass is identical to the first pass, except it just stores the thing there. So it's a very straightforward. I won't belabor the details of the algorithm. It's very straightforward. Once you see this funny max of I2, J2, once you realize what that's doing, there's this mirror imaging across the diagonal, then everything makes perfect sense, I hope. And if it's not, then... So here's this. This is a mouthful right here. This line of code, look at that. I don't usually write code that's quite that terse. Ci of q assigned to w of max of I2, J2 plus plus equals the min of I2, J2. That's a mouthful. Anyway, it works. So it sticks that entry, swapping it if needed. If it goes down here, it's got to put it back up top. So that's the symmetric permutation. So that's chapter 2. Are there any questions about permutations or other stuff, basic stuff? Any last minute questions about the project, by the way? No? I heard that at least one of you had a problem uploading a file that said there was a file size limit.
It's 100 megabytes though.
Oh, 100 megabytes.
Yeah.
Okay.
What's
that?
It's 100 megabytes in Sakai to upload. You can't upload
Okay.
anything bigger than that.
Okay.
It's multiple bytes.
Okay. Maybe there's a different problem, or maybe it was a different setup. We'll check. We'll have to take a look. Okay. 100 megabytes is plenty. If what's that?
Like if I have a helper, I can have like a helper function. Like as long as I take the inputs that you require.
Yeah.
You know, a helper function that has more inputs than that.
Oh, sure. Okay. You can write it. Yeah. The question is, can I have a helper function that does other stuff that has more?
It's easy to find the number of entries in like the mex function, in the mex file.
Uh-huh.
But it's harder. I don't know. Like, cause you can't use the like mex get number of entries in like a source file. Right? It wasn't working for me when I tried to use it.
I could. Yeah. I mean, I could take a look specifically, but
I mean,
yeah.
as long as I have it. I mean, as long as it takes the right number of entries from MATLAB.
Yeah.
Okay.
Yeah. Yeah. Okay, so I have also posted the project 2, if you haven't seen it yet, and I've given very careful instructions this time, so hopefully it'll be completely clear, and if it's not, let me know. Let me explain it just briefly. So it's matrix multiply. Okay. But wait, I've already done matrix multiply. What's the big deal? Well, I made a big deal when we were doing matrix multiply to say, well, no, you can't use dot products because that'll be n squared time algorithm. But guess what you're doing for this project? N squared. Okay. However, what I'm doing is not exactly this. What I'm doing is A transpose B. Now, imagine if A and B are just column vectors. And imagine, too, that these column vectors have sorted row indices. I mean, we're going to exploit that. You have to exploit that in your project. If you do not, you are toast. That's English idiom, American idiom for you are dead, defeated, nothing, worthless. Okay. So if I've got two column vectors, now, that look like they're supposed to be the same length. So there's A transpose, but it's stored as a column vector. All right. Now imagine if these are column vectors of length 1 billion, and they've got 100 non-zeros in them each. Okay, but they're sorted. Now, you could compute A transpose. That'll take order 1 billion time and space. Right? Because you have 1 billion column pointers. You know. Here's an empty column, here's an empty column, here's an empty column, here's an empty column. You know, it's like a dense matrix. Forget it, right? It's ridiculous. It'll take a huge amount of time to compute this. And the demo code I gave you, the test code I gave you for Project 2 will show you that. So instead, it's better to do the multiplication and the transpose at the same time. Don't do the transpose. Okay? And you can do this with something like the merge sort command. Something like the merge of a merge sort. Okay? You've got two columns. All right, and they have sorted row indices. So you look at the first entry of each column and you say, oh, one's smaller than the other. So you don't do a merge. You in fact throw it away because you're doing a multiplication of these two pairwise. And if you see one that has a row index that's smaller than this row index, well then nothing happens because you have 0 times that entry. So you throw the thing away. Well, you don't actually delete the input. Okay, you just skip over that. But when they do line up, you multiply and accumulate. Right, so if they line up, you multiply the entries and add, and the result is a scalar value. Okay, and so this is very fast to do with two vectors. Okay, and the time is order the number of non-zeros in A plus the non-zeros in B. So you might wonder, well, gee, if it's so efficient, why didn't I use it for the general case? Well, the problem with this general case is that you have to do this dot product for every possible output of the C matrix. So if this is actually, say 10 columns and 10 rows by a billion, okay, then you've got to look at every combination of rows, these rows with those columns. In other words, you've got to do order 100 of these dot products. Well, and now I have to expand this number of non-zeros in A and B. That'd be that particular row in that particular column. Okay, but the dominant, if this is let's see, this is K and this is K and this is N and this is M. There's going to be an order M times N component in this because that's the number of dot products you have to compute. And if C is a large matrix, suppose these are two square matrices of size 1,000,000 each. Okay, you've got 1,000,000 squared dot products to compute, which is absurd. So it's a horrible method if C is big and square. But if C is tiny, A and B, A transpose B, I should say, A and B could be huge, but the result C could be very small. In other words, M and N could be very small. So this method using dot products is appropriate if both M and N are much, much less than K. Because there's no time complexity for K in this. But if you take the transpose, you get order K in there as well. And you get order K added to this. So if K is much bigger than Mn, then it'd be better to use the dot products. And in fact, I did this for the MathWorks. And I determined that I looked to see, so I noticed this was a problem, and so then they asked me to do sparse matrix multiply for them. They're not exploiting it yet, because this requires work to do in the parser, right? Because the parser has to recognize that it doesn't have to do a transpose and then a multiply. It's a fused transpose multiply. Okay. And there's actually other conditions. B could be transposed or not. And the result could be transposed or not, and it could be dot transpose for the complex conjugate. There's about 16 different combinations. And then the question is, when do you exploit? Now, you're just doing dot products for Project 2. You're not trying to decide which method to use. But it's hard to know ahead of time. It's kind of interesting. With matrix multiply, it's very difficult to determine ahead of time how much time and space the matrix multiply will take. The only way to do it is actually simulate the entire piece of work and then redo it again. Okay, and so it takes time proportional to the total work, to determine how much time and how much space it'll take, which is asymptotically equal. So you might as well you could imagine it's easy to do, right? Well, it's easy asymptotically, but actually when we look at the factorization methods, it'll turn out to be asymptotically simpler, much simpler, to determine the pattern of the result and the flop count to compute it and such, than it is to actually do the work numerically. Okay, and you'll start that with chapter 3. But matrix multiply, that's not the case, oddly enough. So what I do inside MATLAB, assuming that they gave me the right parse, which they don't yet, they don't exploit this feature, but they will soon, is I just pick whichever method uses the least workspace. Because what you're going to do, and what I did inside MATLAB, is this dot product method requires m times n workspace, which could be enormous. But if m and n are small, then it will be small. So all I do is I calculate, well, how much workspace do I need for the dot product method? I need a full matrix C, but I don't need an order k workspace to do the transpose. So I calculate how much workspace I need for the dot product method. And I calculate how much workspace, how much memory I'll need to transpose A and then do the multiply. And I just pick whichever one uses the least amount of memory. I don't know which one will be faster, but I'll tend to pick this method for when m and n are very small, and it'll tend to be the faster one. So, in fact, picking the one that uses the least memory, there's a nice reason for doing that, because you want the thing primarily to work. And then you would like to go fast. Well, memory, you either have it or you don't. And if you don't, and you try to use it and it's not there, you just don't do it. So it doesn't work. So picking the method with the least amount of memory will tend to be the fastest method, not always, but certainly it'll be the method that'll work where the other one won't, in those cases where it's really a big problem. Anyway, so that's what you're doing for project 2. So take a look at that. You're doing the dot product version. You're not going to do this automatic check. You could if you feel like it. I mean, it'd be kind of fun, but you don't have to. I was a little disappointed. I checked the recent version of MATLAB and I realized, whoops, wait a minute, it's not there yet. Not because, by the way, that I can't see the code in MATLAB. They don't let me look at their code. I toss my code over the fence and they put it in. But you can learn an awful lot about what's inside a code with tick and talk. Tick and talk are the time. Or you just time the code. Tick. You do the work and talk. You get the elapsed time. You can look inside, if you will, and through the time you can figure out what the time complexity is. Is there an order k component in here? And is there m? Whatever. You give it one of these extreme cases, and if it takes a long time, then you realize it's not using this method. It must be using another one. You can do all kinds of things. You can tell whether or not it's using a binary search here or a linear time search there, and because it's the asymptotics. And if you give it a problem big enough to push the asymptotics, you can watch the line, you can watch the curve, you can plot the results, and you can, reverse engineer what's inside. It's like figuring out how many cylinders an engine has by revving the engine and listening. Oh yeah, it's got 8 cylinders. It's kind of like what you do. You can do that with MATLAB as well. See, look at the RPM behavior and figure out what kind of transmission it has or something like that. I mean, I can't do that. I'm not an auto mechanic, but I mean, I guess someone who drives a Ferrari, say, might be able to tell the difference. I don't drive Ferraris. My dad did, actually. He drove a Ferrari. Okay, so I just drive fast code. All right. So the rest of the stuff in chapter 2 is fairly straightforward. How do you compute the norm of a matrix? It turns out to be difficult to compute the 2 norm. And if you don't know what I'm talking about, what is the 2 norm of the matrix? Don't worry about it. We'll talk about that later when you do QR factorization. And then I've got some utility stuff here for reading a matrix from a file. This is a very simple thing to read triplet matrices. And then I have this is useful just that you know that it exists. I have this method to print a matrix. And so there's Spock, in MATLAB you can check to see if it's correct. This thing doesn't actually check to see if it's correct, but it will print it out. And if you start getting garbage, you realize, whoops, something was broken.
What's the brief parameter?
I'm sorry?
What's the brief parameter?
Oh, the brief parameter. This, if you've got a very large matrix and you don't want to see all million entries, then if you set brief to true, it'll print just the first 20 non-zeros in the matrix. See, it'll just print dot. If P goes over 20, It prints dot, 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 and then finishes. And yeah. And it either will print a compressed column matrix or a triplet matrix as it decides, based on the flag here, the ANZ flag. Okay. So that's chapter 2. Now we can go on to some more linear algebraic type stuff, which is chapter 3. And some of this will be familiar if now we're kind of sort of going back by pieces to the very first 2 days worth of lecture where I took that 1 hour seminar and broke it into 2 hours where I gave you kind of the bird's eye view, the big picture of the whole course. And so now in chapter 3 we're going to look at solving triangular systems, which may seem backwards. It's like, well, wait, why are we interested in solving triangular systems when we don't have them yet? I mean, normally you say do an LU factorization, and then you need to do a upper triangular solve, say y equals u slash b, and then x equals l slash b, and you have the solution to the linear system. So wouldn't it make sense to do LU factorization first and then the upper and lower triangular solve? Well, in this sense, yes. But what we're going to see is that for two reasons. First of all, this is a simpler problem than this one, so it makes sense to talk about this one first. The other thing is that I'm going to use the triangular solve to do this, to do LU factorization, to do the triangular factorization, to do Cholesky, to look at QR. We're going to need to know how the triangular solve works, because this is like Oliver and Oliver Twist, right? This is the little guy who just finds himself everywhere in the whole book. The triangular solve, right? This is the main character of the book, of the novel, of sparse matrices. Okay. There are many ways of doing LU factorization. All right. Not all of them rely on this, but the simplest one, the one I chose for the book, does use this. So that's why this is very important to look at first. We're going to look at where B is a dense vector. That's the simplest case. That's not what I use, though, in LU factorization. What I use in LU factorization to actually compute L and U, you have to do n triangular solves. You're going to have B is going to be a sparse vector because it comes from the columns of A. So when you do the triangular solves with columns of A, you'll end up computing columns of L and U. That's getting ahead of ourselves, though. So we're just going to say, well, let's imagine we just have this problem here. And let's imagine, so we're doing a triangular solve. We have this linear system, Lx equals B. And how do we solve it? And where B could be, first case, it'll be a dense vector, and then the second case where it will be sparse. Now, we want to pick a method that's suitable to our data structure. Okay, there's many ways. In fact, there's essentially is there an infinite number of ways? I guess if n is a countably infinite number, if it's an n by n. So if n is finite, there are a finite number of ways of solving this lower triangular system, but it's a combinatorial enormous amount. Okay, because I can slice and dice this matrix up in many different ways, recursively even, and different pieces can be cut differently, and I'm going to show you now how to solve this triangular system. I'm not going to start by saying, well, here's the way to solve a triangular system. I mean, you could do that. You could say, well, I know x1, solve for x1, and then remove it from all the equations from where it appears, and I could explain it that way. But that's too constraining. That's actually how it will do it for the L, but not for other solves. So I'll need more general methods. But I'm not going to explain it that way. I mean, you can think about it that way, but I'm going to explain it in a better way that gives us more flexibility, and that's using blocks matrix multiply. Oh, but wait, block matrix multiply. I'm trying to solve a linear system. I'm not trying to do matrix multiply. Well, yes, but the multiply, again, tells you how to solve the linear system. So let's take this matrix L and let's slice and dice it like this. And if that's not sliced and diced enough, we can always do this recursively and take L22 or L12 and we can slice it further recursively in any shape we like. Now, I've not put any dimensions on these except, well, these are column vectors, 1 and 1. Why? I mean, that's just for the sake of argument at the moment, I'm just assuming that X and B are column vectors. I'm assuming that L is square for the moment. But I haven't yet said how big these pieces are. I have to cut this the same way I cut this. Okay, so I could call this N1 and N2. This would be N1 and N2. So N1 plus N2 equals N. And I haven't yet said, I'll use a different symbol here, I haven't yet said how I'm going to cut BB, which would be the same way I cut this. So if this is N3 and N4, N3 and N4, then also N3 and N4 add up to N. And then take your pick. You can basically pick N1 and pick N3 any which way you like. And you'll get a system. Now, in this case, I'm never going to, let's see, am I ever going to pick? I'll end up not picking any N1 and N3 that differ, but they can be, I'm going to choose them to be equal, but they can in fact differ. So this gives us a lot of flexibility, and then as we look into the pieces that we need to do, we'll realize we can also subdivide it further. But let's then forget for the moment how it's sliced and diced. It's just this is just a 2 by 2 block matrix multiply. So we can write the following. We can write that L11 x1 equals B1. And then we can write L12 x1 plus L22 x2 equals B2. So I've just pretended that my matrices are just 2 by 2 scalars, or 2 by 1 scalars. But in fact, they're not. They're whole matrices themselves. They're submatrices. So this is what I have. And so what can I do with this? Well, there's lots of things I could do with this. Depending on how I slice and dice it, it will greatly determine what kind of matrix equations these are. Now, what I would like to do in this lower triangular solve, Lx equals B, if I assume that L is stored as a sparse matrix in compressed sparse column form, which is a big assumption, right? There's lots of ways of storing a sparse matrix. Okay. But if I make that assumption, then I have easy access to the columns of L, but not to the rows of L. I don't have, this is a non-presidential matrix. I don't have the rows of L. Okay, that's lame. It's the Lincoln matrix, not the Roosevelt matrix. So I'd like to slice and dice this, and one of the ways is to choose N1, N3 to be 1. And so now what happens is I've got L11 x1 equals B1. I can solve this directly. This is a scalar. I can take x1, step 1 of the algorithm could be to solve this. x1 is just B1 divided by L11. B1 over L11. or we say in English, or American English, we say B1 divided by L11. I guess in Indian English you'd say B1 by L11, right? So you drop the word divide, but that's a big word there. We don't like to drop that. So I'll either say B1 divided by L11 or B1 over L11. So I can solve for X1, then I can plug it into here, and now I have a new system, L22 X2 equals B2 minus L1, 1, 2, X1. Well, now what can I do? Well, step 2, I can compute this, because I have X1, I know B2, and so what does this look like? Well, if L11 is a scalar, and N1 and N1 are both equal to, N1 and N3 are both equal to 1, then this is a vector of size 1 by n minus 1. And it's a column vector. In fact, it's the first column of this matrix L. Right here. All the entries below the diagonal. So this is L11, and the remainder here in this column is L12. X1 is a scalar, and B2 is the rest of the B matrix. The rest of the B vector, I'm sorry. It's of size, and this is of size 1, and this is of size n minus 1. So now the question is, how do I do this efficiently? Can I do this efficiently? Yeah. If this is a dense vector, okay, I can index it however way I like. If this is a sparse vector, this is a scalar. X is, and it's easy to find because X is a dense vector. The only thing that's sparse is the column of L. Okay, what do I have to do? I have a column of L. I have to be able to have quick access to the diagonal, because I need to, in constant time, I need the diagonal entry. Then I need quick access to the rest of the column. And if I have that, I can go through this sparse column vector. I can iterate across the non-zeros, multiply that by that scalar, and then directly do a scatter operation, right? It's a scatter because I'm taking a sparse vector, multiplying it by something, and then adding it into a dense vector. So this will be a scatter operation, which is very efficient. I mean, it's got irregular memory access, but it's asymptotically efficient. And it respects this data structure for L. So the only constraint on the data structure for L, if I'm storing it as a compressed sparse column matrix, is that I would require that the diagonal be easily found. What does that mean? Well, I could either store the diagonally separate in its own vector, or what I assume in C-sparse is I assume that if you're going to do a triangular solve, that the diagonal entry of each column has to be the first entry in each column. And that's not going to be a problem because the typical way where these triangular matrices come from is from, say, an LU factorization. And the LU factorization will respect that. It will actually create an L that behaves like this. The diagonal entry will be the first one here. The column below it does not need to be sorted. It could be, but it doesn't need to be. And in fact, the LU factorization in the book will produce an unsorted L. Every column, the row indices will be out of order, except the diagonal will be the first one. Okay, so it just connects perfectly to this triangular solve here. So I can compute this. So now what do I have? I've got L22 X2 equals B2 prime, if you will. I've got a modified version of the B2 vector. This is an n minus 1 by n minus 1 system of equations. And how am I going to solve that? Well, any way you like. Yeah, Ed.
Are we also assuming that the diagonal is fully populated?
Yeah, if it's not, you'll get, the question is, are you assuming the diagonal is fully populated? Yeah, because if you don't, you divide by 0.
Yeah, that's why.
So yeah, I'm assuming not only is the diagonal the first entry, but it's always there and it's always non-zero. And if it's not, you won't get the right answer. You won't get any kind of answer worth anything. It's not. You can't use it. In other words, this triangular solve only makes sense if the diagonal is non-zero. Because you can't divide by 0. Unless you're in grade school in California, then you can. Yeah, you can. Because I got a sample test from the California school system, mathematics test, and they ask questions. What's 6 divided by 2 and 3, and all that. And what's 60 divided by 0? My daughter had this sample test with an answer key. And asked the question, what is 60 divided by 0? I kid you not. I have a copy of it. Only in California. And yeah, actually, her answer was quite intriguing. I mean, it had answers like 0, 10, 60. Why not? All of them. Her answer was rather intriguing. Her answer was 60. Which makes, why not? She says, well, you can't do it. You can't take 60 and divide it by 0. So the number 60 remains undivided. Why not? It makes sense, right? The answer key said 0. And you know probably why? When you punch it into a calculator, you get 0. Well, you get lots of zeros. It sort of goes, bing, 0, 0. It says it's really 0 because it flashes at you. 0, 0, 0, 0. I kid you not. I actually have this. So you can't divide by 0 unless you're in California in grade school. Then you can. So we're not in California. We're not in grade school, so we can't divide by 0. If you're curious, I could show you this. I used to have it posted on my door. It's hilarious. Okay, so but enough making fun of California. I mean, my wife is from California. I can't make too much fun of California. The land of fruits and nuts. Oh, I just said I was not going to make fun of California. Anyway, so how do we solve this remaining n-1 by n-1 system any way we like? Any way we darn well please. How could we do it? Well, we could do it recursively. I mean, it's another system of smaller size. How do we solve it any way we like? Here's one way. So if you do it this way, then you'll get, now what will happen next is that to solve this, you'll divide by the first entry, the 1, 1 entry, the L2, 2 matrix, which is the second entry. You divide by this and then subtract off the second column and so forth. So if you do this, if you solve this algorithm, use this algorithm itself recursively, then you get a conventional algorithm where you do exactly what I said at the beginning I wasn't going to do. You take this scalar, you solve for x1 by dividing, and then you take this x1 and you remove it from this, you multiply it by the L vector. So you take it and remove it from all the other equations in which it appears, and then you repeat with the second unknown. That's exactly what this is doing, but it's not explained that way. It's explained instead with block matrix multiply. There's a lot of other ways of doing this. I mean, for example, I could take this and slice it in half. What if n is a power of 2? What does this become? This becomes its own triangular system. This becomes a vector times, this is a matrix now, and this is a vector. Well, we did matrix vector multiply. We know how to do that. L1, 2 is an n over 2 by n over 2 matrix. And there I've completely confused the Indian students because I've used by and over in the same sentence. It's a matrix of half the size in each dimension times a vector. And then this is also a system now the same size as this one. So I've taken the matrix and I've sliced it this way. I'm not doing this in the book, but you could. You could cut it in half here. And now you've got a triangular solve to do here, recursively. A matrix vector multiply. And then another triangular solve. Why not? That works. And that would work in the sparse case too, just fine. You'd only have to be sure to figure out where to find this boundary. And that's not a problem. If you say assume the columns of L are sorted, when you do this triangular solve, you're working through and you stop when you find the boundary. And you just make a note in some work vector of where the boundary is. And when you do the matrix vector multiply, you pick up at that boundary. And then you do the matrix vector multiply. And then you do the triangular solve. That's very easy to do. if the columns of L, say, are sorted. So there's lots of ways of solving this, but this is one way. And when you then, okay, recursion is a problem, only in the sense that it leads to stack overflow if the depth of the recursion is large. And the depth of this recursion will be n. And n is a big number. Okay? So we want to unroll the recursion and write this iteratively. Right? So, but you guys are computer scientists. You know how to unroll recursion. So here's this picture now. I have now L11 is a scalar, L21 is a column vector. I have these two equations, which are already written this on the board, so I guess I don't have to do this again. We can solve the first system and then recursively solve the second one. And then unrolling the recursion, this is what we get. Except with one extra twist. And the extra twist is this. Let's suppose we make the claim that, well, when I'm done with the solution, I don't need the B vector. Let's suppose that's the case. If that's the case, then once I use B1 here at this step, I no longer need it. If I don't need it at the end of the algorithm, at this point I don't need it in the computation. So I can overwrite B with X. That's kind of handy. And over here, likewise, once I've updated the B2 vector, I don't need the old B2 anymore. Okay, and I have a new vector B2 now, which then if I recursively assume that this algorithm is going to overwrite B2 with the solution X, then that will work as well. And so this algorithm can overwrite its input with its output with its input. No, it can take the output and overwrite the input. So I can solve it in place. And so that's what's going to happen at the beginning. I'm going to assume that, okay, B just gets copied into X. And then I can just take X and divide it by the diagonal. And then here I do the subtraction. This X really is the right-hand side. No, this is the X, and this is the right-hand side that's being updated. But I'm just going to assume that they're overwriting each other, and I no longer need the right-hand side. So I just copy it over and then just work with X. So in the sparse case, when you're going down this column L1, 2, of course, you can only have to iterate over the non-zero values. And so that's what this pseudocode says. For every row index for which Lij is non-zero, do this. Okay, so now do you see where I've gotten this algorithm? This algorithm by itself is easy to understand if you just think of it in terms of a linear system and you're removing equations and substituting and subtracting and off and things like that. But it's also equally important to be able to think of it this way as a block matrix, as the expression of a block matrix algorithm. Okay, it's very important to understand both, in fact, and this is actually more important because this kind of derivation I'm going to use over and over and over again. So if you don't understand what I've written on the chalk here and what's written in the book about it, which I belabor in great detail in the book for this case, then you won't understand the rest of the book. So please make sure you understand what I've done here, algebraically and computationally. And if you don't, come see me and we can hash it out some more. And trust me, some of you will stumble over this, I know from experience. So please come and see me when you stumble. I'm here. That's what I'm here for. So this is the pseudocode then. And then if L is stored as a sparse matrix where I assume that the LJJ entry, the diagonal, is the first entry in each column, then here's the code. Very simple. I mean, the code just mimics the pseudocode directly. I just go through each column, I divide by, here's the first entry in the column, and I assume, I don't even check in this code, I assume that's the diagonal. I mean, if it's not, who knows what this is going to compute. And then I just iterate through, you notice here it's LP of J plus 1. This is then the entries below the diagonal. And this loop here can operate in any order. We've got to have the diagonal first, but these entries here, it doesn't matter what order we see them in. So there's the lower triangular solve. And I'm out of time at this point, but what we'll do next is we'll ask the question, what happens if we want to solve L transpose X equals B? And here is where this kind of matrix thinking will be very important. and I'll derive this algorithm next class. But if you don't understand what I've done here, please review it. Please come and see me, and we can talk about it. So, see you guys on Wednesday. Thank you.